Morning, guys. So yesterday we started looking at the main key term. This one here was isotope. They always like asking this question here, define isotope. Whenever I see iso, I think something is the same. Tell me what's the same about them. So as you're defining this one here, an isotope, isotopes of each other are exactly the same element. What is it that makes the element that type? Well, that means it's actually the same number of protons. That number can't change. But they are variations of each other. They are different in some way as well. For isotopes here, they are the same element with different mass. And again, I would just qualify, well, how do I know that they have different mass? Well, the other massive particle we have are neutrons. Neutrons don't have any charge, so they're all going to be equal positive and equal negative. But in some sense, there are going to be some that are lighter, some that are heavier. We did chlorine in a little bit of detail here. Although chlorine has two natural isotopes, we have chlorine 35, we have chlorine number 37 here. So those are the two versions of chlorine. On the periodic table, unfortunately, we're only given one spot to actually list the mass of chlorine. What they've actually done for you is they've actually made this one here a weighted average. It's not just a simple average, oh, let's take the two types and divide by 2. The average would have put you, simple average would have put you 36. But what they've done is they've skewed the average. It's now leaning more towards, let's say, 35.45. It's actually the one that's actually more common, because in our universe, just because you do have the 35 form and the 37 form doesn't necessarily mean that they have to be equally common. If that were the case, the average mass here would really be closer to 36. What we had found in yesterday's lesson here, in fact, we actually have, for every 3 chlorines that are 35, we actually have 1 that's 37 here. If you backtrack when we were doing our sort of PNE analysis, we were sort of saying how many protons, how many neutrons, electrons, if they don't specify the mass. So if they just say, oh, here's chlorine, how many protons, neutrons, electrons, you're more than welcome to just go to your periodic table and say, well, because this is a weighted average here, I'm going to take the 35 type. If they specifically say, do it for the 37 type, you do the same PNE analysis, but you do it for the type that they actually give you. And just to show you, sometimes we actually get it wrong. In regular grade 11, grade 12, they don't actually have 2 decimal places. Sometimes this average mass, this weighted, they actually give it to you as 35.5. If they didn't specify what the average mass I'm supposed to use is, if I did my regular rounding, 35.5 is going to be 36. I totally have a version of chlorine that doesn't exist, but so be it. That's why I know from the periodic table. I know I would, in that case, there's 19 neutrons, but I would still mark you correct for that case. So if we're not told the average mass here, just take it off the periodic table. You answer the question based on that. If they do specify the mass number, definitely do the PNE analysis, counting how many of each based on what we have. That weighted average formula was one that you had to memorize, so I'm just going to repeat for you here. How do we weight it according to our abundances here? This is what our periodic table does. Basically, it's mass percent plus mass percent. Especially if you have more than 2 types of isotopes here, you just keep tacking on mass percent, mass percent, mass percent. Right? So make sure you know how to do that formula there. It's nice when you have the only 2 types. I can put X in for the proportion of one type. The other type would be 100% minus X. Today we're also going to look at sort of reactions of the nucleus here. These reactions here are actually different from the reactivities I'm going to do for the rest of the course. So just treat these as a slight exception here, because what's going to happen here is because the nucleus itself is actually reacting, where we would have been, let's say, chlorine on the left side, well, the atom has to be conserved, we're chlorine on the right side. In this nuclear chemistry here, we may be chlorine on the left side, but we actually may totally not be chlorine on the right side. We actually change from one element to the other element. So we're going to introduce this section here. This is introducing a little bit of nuclear chemistry, or nuclear reactions. I'm going to first qualify, well, what are the reactions that we're used to? Let's think about those reactions: synthesis, decomposition, replacement, all those. What have those been? In this case here, those ones there, most reactions are chemical, right? In fact, majority of our course will be looking at chemical reactions outside of this lesson. When we say that they're chemical reactions, what they involve, most reactions are chemical, involving, essentially what's happening here is a rearrangement of electrons. So basically electrons are moving, oh, I used to be bonded between this thing, and now this bond broke, and then now the electrons move to attach these 2 other atoms together here. It's electrons that are moving around. So what's happening here is some bonds break, while others form. Right? That's actually what's happening. What's implicit in that statement, however, is the atoms remain unchanged. That was actually the reason why we actually did our balancing. I want to make sure that conservation mass, all the masses are accounted for, no atoms vanish, and no atoms just sort of appear out of nowhere. So let me just demonstrate for you a chemical reaction. So let's imagine we have H2. We're going to react it with Cl2, and I tell you the reaction is going to become 2HCl. All right. So if I just draw a picture here, let's draw the H atoms here. It's diatomic. H as a radical is unstable, right? It needed to pair up that electron. For chlorine, let's draw this in red here. Next year, we're actually going to come back to the fact for these to actually react, these ones here have to be on a collision course. They have to collide. They have to hit each other. They have to contact each other. If they're put totally separate, they're never going to be able to collide. What's going to happen here is upon colliding, what can happen is we're going to actually use some of that kinetic energy from the collision to actually break these bonds, to actually separate those electrons. We're going to see in chapter 4, it's 2 electrons actually make up a bond. And I'm actually going to create a new attachment, create a new bond between H and Cl. It's like my electrons have just moved from between these 2 elements here into connecting the H and the Cl. At the end of the day, we're going to have an H bonded with a Cl in both cases. This has been a chemical reaction because I now have a new proportion, a new compound, a new combination. And this one here, although it will represent hydrogen and chlorine, this one here will have very different properties than the elements itself. So that's all that's happening in a chemical reaction. What I'm showing you here is, notice that if I'm hydrogen on the left, I'm still hydrogen on the right. If I'm chlorine on the left, I'm still chlorine on the right. So in that case there, my atoms were conserved. That's why we had the balancing. In today's lesson, we're not doing this. In today's lesson, we're not just looking at electrons just moving place to place. In today's lesson, we're going to actually look at the atom inside it, and we're going to say, what could happen to this nucleus? Upon alpha decay, beta decay, how can it actually convert? Maybe I'm chlorine on this side, but I'm actually not going to be chlorine on the other side. We'll see how the balancing works out in that sense. So as we did talk about isotopes here, some isotopes are radioactive. That's why upon a mixture, usually one is far more abundant than the other. Some isotopes are radioactive. For that reason, you can actually call them radioisotopes if you like. Radioisotopes, so they're radioactive. And what they're going to do is they're going to actually give off radiation. Radiation is a very general term. It could be particles, it could be energy, and the whole notion here is by giving off this radiation, by giving off what's keeping it from being stable, it's going to form more stable nuclei. For some reason, it was unstable to begin with, and by doing this radiation, by releasing these particles here, it ends up becoming a more stable state. We're going to start from the sort of least strength of radiation here, which is alpha decay. For alpha radiation or alpha decay, really for this stuff here, you just need to be able to identify, well, what is an alpha particle? And then you can predict the rest. For an alpha particle here, an alpha particle is actually a helium nucleus. So let's just do this as a quick aside here. If I take a look at helium on the periodic table, element number 2, 4.00, I can draw the Bohr model for this. So helium, I should have 2 protons in the core. If I weigh a mass of 4, you're going to find for the fairly light things, the proton and neutron number are very similar. It's only when we start getting into row 4, row 5 or so, as we get so many protons, we actually will need more neutrons to have a better strong nuclear force. More on that later on. A helium itself should have 2 positive. It should have 2 electrons. You know from previous courses, well, the first shell can only hold 2. Perfect. That's a helium atom. That itself is not an alpha particle. The alpha particle is actually just the nucleus part. It's just the center part. So if I were to give you the numbers for alpha particle, the alpha particle does have the 2 protons that helium has. It does have a total of 4 units of mass, so that's a 4. In reality, a helium nucleus would have ditched these 2 electrons. This alpha particle here would actually be positive 2. But what we're going to see in this stuff here is we're getting so weird chemistry anyways that we're transferring one element to the other element. We're not really going to worry too much about this positive. If you remember a couple lessons ago, Rutherford actually sent these particles into gold foil. This charge is actually implied by this lower left corner as well. So yes, the charge is important, but usually this is weird enough that I usually just don't write the charge there. Let's try it out here. So just as an example, I'm going to give you here, we have Radium-226, this one here undergoes alpha decay. Can you predict the products? So in the past, if this were a chemical reaction, I'd say, great, you're radium on the left, you're going to be radium on the right. But in this case here, because it's a nuclear process, what we're going to actually emit off is actually an alpha particle. For an alpha particle, you can still use the alpha. Sometimes they even use helium, because I know that's what an alpha particle is. The important numbers for alpha particle is 2 protons, 4 whole units of mass. The question is, what's the other daughter isotope? What's the remaining part? So let's see if we can fill through the blanks here. Sometimes chemists are lazy here. They just say radium-226. How come they didn't give you the atomic number? Well, again, if you know what the symbol is, that to be radium, you have to be element number 88. I can actually fill in that 88 myself. And in this case, what's happening, I can just draw you a picture of this. To be radium, I have to have 88 protons. Careful, the 226 is a total mass. So if I did 226 minus 88, I know this one here happens to have 138 neutrons. That's the other core particles. We'll come back in tomorrow's lesson here to take a look at electrons. It has a whole host of electrons, but I don't really care about those ones in this lesson. What I care is, for some reason, this is unstable, and undergoing its radioactive process, it ends up shooting off a alpha particle. It shoots off something that has 2 protons and 2 neutrons. For my daughter isotope then, I'm going to actually have less protons. I'm now only going to have 86 protons left over. I had 88, 2 of them got lost, so 86. I lost 4 whole units of mass. I lost 2 of these protons, that's why I have 86. 2 of these neutrons here, now I'm going to be 136. Or you could have said more simply, I have 226 total. If I lose 4 units of mass, if I add up those two, double check my math, that should be actually 222. Element number 86. And now, again, this is really weird chemistry. In this case here, I've just converted from being element number 88. Now my proton number is different. What is element 86? This one here is actually radon. I've actually totally changed my element because my proton number has actually differed. So what's nice about these nuclear reactions here is, although your atoms are not conserved, the protons have to be accounted for, the neutrons have to be accounted for. So for example, if I have 88 total protons, if I'm told it's alpha decay, I know 2 of them leave, well, the other 86 has to still be somewhere. If 86 still is in the same element, I'm now radon, I'm now a totally different element. So mathematically, you can just go, this lower left number here, 88, if I go 2 plus 86, great, that's 88. If in total I had a mass of 226, that total mass had to go somewhere. The protons and neutrons have to be somewhere. Some of them actually got lost with the alpha particle. That's 4 units of mass, 2 are protons, 2 are neutrons. That means the other 222 plus 4 is actually 226. At least that sort of math is conserved. So we're not balancing in terms of number of particles anymore. The particle number actually changes. This time we're actually converting the actual element itself. I mentioned an alpha particle here is the weakest form of radiation. Alpha particles can be stopped by definitely like a piece of paper. GOFA, we saw that sort of interaction as well. As we step over to beta emission here, beta emission is roughly 100 times more penetrating than alpha. So in the Greek here, it's sort of like the, did I put 1 there? Yeah. It's sort of like just the alphabet here, alpha, beta, gamma. So it's like A, B, C, and they're just sort of giving a different lettering to it. So here I have beta emission or beta decay, many different names for it. For beta emission here, a beta particle itself is actually just an electron. You might say to me, well, I thought this was not the electron's reaction, whatever. The trick here for beta emission here is, where does this electron come from? For beta emission, see if you can place yourself here, a neutron actually becomes a proton. One of those core particles that were neutral actually converts itself into a proton, and in the process of doing that, releasing an electron, and that electron there is called a beta particle. This one here actually gives off a bunch of other stuff. If I wrote just that reaction for you, I can say 1 neutron actually became 1 proton, 1 electron. I know this reaction produces like antineutrinos, things like that. We're not going to worry too much about the rest of it. We're going to focus mainly on, well, the neutron has become a proton and an electron, which comes back and explains, if you really looked into the details on your data booklet, it says a proton weighs 1.007 atomic mass units, a neutron is 1.008. We've up to this point just been 1 for proton, 1 for neutron. In this case here, the neutron, because it's actually made of a whole bunch of other stuff as well, a neutron is ever so slightly heavier, but electrons are very low mass, so therefore it's not going to be by much. So let me again just draw you the picture so you understand what's happening. Let's use our same radium. It's possible that this one here actually undergoes beta decay instead. You don't have to predict, does it do alpha, does it do beta, but upon being told it does one or the other, you should be able to predict the others, or they can even give you, well, the beta particle over here, and you can recognize that as beta. So let's draw a picture. We have 88 protons. Earlier we set this one here at 138 neutrons. This one here, I'm going to just mark off for you, yeah, there's going to be a lot of electrons in the outside shells. I'm not worried about those electrons. What I'm worried about in this case here for a beta emission, for some reason the nucleus is unstable. The center is unstable. And what's going to happen here is one of these neutrons, one of these neutral particles, is going to convert itself to become a proton. How many protons would I have then? I already had 88. If I gain one more, now I'm going to have 89 protons. Again, your element has changed. It's the proton number that made you this element. In this case here, let's look on our periodic table. Periodic table says element number 89 is actually actinium. Again, it's weird. I've just converted elements again. So now I was radium on the left side. I'm actually actinium on the right-hand side. My mass, however, a neutron and a proton are roughly the same mass. If I rounded that just to 1 sig fig, you'd say 1 anyways. It's practically like the mass didn't change. But we know something was released. It was actually a beta particle that was released. You'll notice as the neutron becomes a proton, where it's going to actually spit off an electron, that electron is called a beta particle. That electron is identical to the electrons that used to be out here as well. But the kicker here is you see that that electron actually comes from the nucleus. That electron is not one of these from the valence shells and the different orbits. That electron wasn't in existence before. It was only because of this decay that electron got released. Let's see if we can do the math here. What numbers does this beta particle or does this basic electron have to have? Well, electrons practically have no mass, so 0 is okay. 0 plus 226 is 226. What should I put here so that the math works out? Because I know every time I beta decay, I'm going to pick up one extra proton, I would actually need to put a negative 1 here. So that 89 minus 1 is going to be 88, and we're going to call this one here, this is the beta particle. It was an electron from the nucleus. Notice usually we would put on the lower left corner, usually we put the atomic number. Lately in science, they've actually created what's called anti-hydrogen. They've created an anti-proton. This is not it. That negative 1 is just convenient math, convenient placeholder for us, so we can just simply go 89 minus 1 equals 88. So there we go. That's alpha decay. That's beta decay here. Really weird chemistry because we were radium before, and then afterwards the proton number is now different, and I'm now actually not radium on the other side. As we get to the third type of radiation, this is the strongest type of radiation. This is now called gamma radiation, or gamma rays. Gamma radiation is actually just pure energy. So a gamma particle here is just energy. So for whatever reason, the nuclei is unstable. To radiate away energy, to get rid of all this energy, it puts me in a lower energy state. In general, in our course, the lower the energy, the less can go wrong. So the more stable you're going to be. So let's take our radium again. Seeing as we have some familiarity with it here. We have radium. I'm going to mark it off with a star to show you that this is unstable. I'll hint at why it's unstable in a second here. Radium is 226, and what I'm told here is radium undergoes gamma radiation. We'll really only see gamma radiation. It's really energetic on the EM spectrum. We'll see it in deep space. We have pulsar stars do gamma radiation. We use gamma radiation for like chemotherapy. If you like the Marvel movies, Incredible Hulk was also gamma radiation. So really, really high energy. But in this case here, for gamma, because it's pure energy, there's practically no mass to it. There's no protons that are being released. This is actually the strongest, the most penetrating radiation, but it actually doesn't change me from radium. I was radium on the left. I'm still radium on the right. I'm still 226. It didn't change at all, but what's missing here is now going to be the star. So the easiest to predict, but this one here, we can refer to this as the ground state. The ground state means lowest energy, and I want to always have this sort of implication. The lower the energy, the more stable things are. You need energy to do things, and if you don't have energy, not a lot can go wrong. So the star becomes the non-starred form. I'm going to hint at what's making this thing here unstable. So we know radium here has 88 protons, has a lot of them. I'm not going to bother drawing all 88. Usually in the Bohr model, I just list 88 protons like that. Let me just zoom in at a couple protons. Let's say for one area of the nuclei, let's say the protons here were sort of neck and neck. They are going to definitely be very close together anyways, because the nucleus is so tiny in comparison to even the atom, which is already small. We know protons themselves really hate each other, right? Like charges always want to repel away from each other. part of the job of the neutrons is to try to space out the protons. So if I have a picture where out of the 88 protons, I've drawn 3 of them, and let's say the neutrons here, they were all sort of stacked in on one side, I could say, wait a second, these protons are closer than they necessarily need to be. If I can somehow sort of interconvert, this is the nucleus of the atom, by the way. If I can somehow, nuclei is plural for nucleus, if I can somehow squeeze those neutrons in between the protons, let's say later on, if I zoom in at those same 3 protons, I know it's not by much, but if I can squeeze those neutrons and actually separate out the protons even ever so slightly, that's going to be a slightly lower energy state, slightly more stable. Anything extra, I can radiate it away, and it's that energy that I actually radiate away. That's the strongest radiation. This is about 100 times. You can make a note to yourself. This is the most penetration power. Penetration. You'd need sort of meters and meters of cement or even heavy-duty lead to actually stop this radiation. Most penetrating. So alpha is weakest, beta is medium strength, and this is most penetrating power. So that's hinting at how come the nuclei could be unstable, and now why would I be more stable? Even if I can separate it ever so slightly, it doesn't seem like much, but we're going to find that even that added distance here will help. We also needed the added neutrons here to be our strong nuclear force. Basically, I imagine an imaginary set of hands here that's constantly squeezing the center together. The center is always pushing away from each other. The positives all hate each other, but it's the strong nuclear force that's keeping it together. So really weird chemistry here because we're dealing with reactions of the nucleus. We've introduced sort of alpha, beta, gamma. Next year, there's the optional unit here on nuclear chemistry where you can actually, or nuclear energy. So we're actually going to talk about fission and fusion reactions. Those are a little bit more general than just these basic decay reactions. But even in that case there, we can do the same math. I can do like top number plus top number gives you top number. Bottom number plus bottom number gives you bottom number. So at least that part there is conserved. Last little bit for today's lesson here is we're going to now apply this to sort of our scientific context here. Where might I see this in science? We're going to do an application to geological dating. Romantic rocks? No. Okay. So geological dating here. We are looking at, first thing, radioactivity. If you think about the alpha, the beta, the gamma, radioactivity is a random event. So you can't actually predict when it's going to happen, how long until the next event happens. There's going to be a probability that comes into this. So radioactivity is a random event. So we cannot predict which atom will decay, let alone when it will decay. So let me just point that out to you here. If I just have one single atom and I tell you, oh, this is radioactive, because this is just a single atom, I can't actually make any predictions. This one here might decay when I'm not looking. This one here might sit around for a million years and not decay yet. That's completely random. However, because of this random event here, fortunately for us, we usually don't try to make a prediction on a single atom. We usually have a bulk sample. We usually have many, many atoms. Same story is true. You can't put your finger on it, you're going to be the next one to decay, or you're going to be the next one to decay. All that I know that is in this bulk sample, in this majority, some of them are going to start decaying away. Some of them are going to start popping. So let's say as I watch this one here, I happen to notice, oh, this one decays. I wait a little while, oh, it happened to be this one decayed. I wouldn't be able to predict that from the start. I wouldn't be able to say, oh, you're going to be the one that decays next. Here's how long it's going to take. But what I can do is, because I have so much sample, I'm going to just sort of in general, I'm just going to wait. I know some of them are going to decay. And in fact, just for convenience, let's imagine this one here is 100% of your sample. What I'm going to do is I'm going to wait for what's referred to as a half-life. Another term you want to note here. Half-life, they can use the symbol T-half. We're going to use K as well for that variable. Half-life is actually the time needed for half the sample to decay. Now, a slight simplification here, we're going to pretend, let's assume we have 100%, maybe even 100 grams. Let's assume when we have 50 grams. Right? Now, in some sense here, mass shouldn't disappear. What I'm saying here is maybe the radioactive mass, the radioactive chemical, has actually converted into something else. At least the radioactivity, the intensity of the radiation has actually dropped by half. The time it needs to do that is referred to the half-life. Now I have, let's say, 50% of the radioactive material present. Maybe the other 50% is now interconverted into non-radioactive mass. So that's a half-life. Turns out every element has a different half-life. Some half-lives are on the order of seconds. Some half-lives are on the order of many millions of years. So it's characteristics of the element. So if I weight this half-life here, 100% here, the radioactivity is expected to drop to half. What if I weight another half-life? I'm going to use K for that symbol just for simplicity here. Well, I did lose 50% at the beginning. You might imagine if I lose another 50%, now I have 0 of the radioactive stuff left. But in this case here, because radiation is random, at first I had a bigger sample. So if half of those decay, obviously I have 50% left over. Now with half the sample, I don't have as many particles. Even if these ones here start decaying, oh, that one went a little bit later, oh, this one went here. Because I have half the number of material to actually start off, only half of this 50% will actually decay. If I weight that same interval, this one here will actually only be 25%. What I'm sort of suggesting to you here, not only is this sort of probability, this random event notion here, is even though the decay rate is constant, we're only going to lose half every time we weight a half-life. What I'm hinting at here is this is an exponential curve. So if I plot it here, what is sort of the relative percentage or the proportion that you have left over as I weight in terms of time? At first, you have 100%. At first, you're going to have the most radioactive sample. We know some of them are going to decay away, although you can't make a prediction on a single atom. If you weight one half-life, right? So I'm going to say this is 1 unit of half-life. That means I'm going to be down to 50%. So when I had a lot, as some of those decay, this one here is going to steadily drop off here. It's actually going to drop off faster at the beginning. But by the time I'm 50%, you notice I have less sample to decay with. The decay rate is going to be constant. If I wait another half-life, doesn't necessarily have to be 1 second or 2 seconds. I'm just doing increments of half-life here. I have half the sample. The decay rate is constant. I'm now going to have 25% of it left over. This curve here just steadily drops off. In some sense here in the math here, this curve here never actually makes it to 0. It's asymptotic. However, by the time it's dropped off enough, maybe I sort of lose sight of it, right? You can make a note here. Never actually reaches 0. But again, sometimes we sort of lose sight of it, and it's decayed enough. This is the problem with a lot of like nuclear power plants. After I run through my reactions and the leftover products themselves remain radioactive, what do I do with all this radioactive waste? Usually, if it's very low-level waste here, I just wait it out the half-life, if it's not that long. If it's a really long half-life, if it's a million years, nobody has the time to do that. So far, the only solution has been, oh, let's just encase it in glass, let's encase it in cement, and let's dig a really deep hole, let's put it in the earth, hopefully in a place that doesn't have earthquakes and whatnot, and let it wait it out the half-life there. I know not the best solution, but that's sort of what we come up with. Because this is based off of radioactive decay, in your data booklet here, it's going to give you this formula. It actually tracks for you the amount at time t is based on your initial amount. If I have more at the beginning, it's going to decay. We're going to think in terms of the change rate as 0.5, so 0.5 for half-life. And on the top here, I'm actually going to have 2 times. The first time is actually going to be the actual time that I wait, but I'm going to be thinking in terms of half-life. So this is a formula sheet. You don't need to memorize it, but we're going to practice through a quick question or two. How do we use this formula? So this one here, I think that this is the final amount remaining, or you can say this is the amount at time t. So if I wait 10 years, how much is left? If I wait 20 years, how much is left? Whenever in science here they have this little naught symbol, that naught usually means it's the initial. So this is your starting amount. This is how much you began with. This is at time 0, when you just started your clock. Again, because we're going to be thinking in terms of half-lives here, half is going to be your the rate in this case here. The top t is the actual time. I'm going to call this the elapsed time. This is you run the clock. I don't care if your half-life is a second or a million years. This is how long I'm actually waiting. But what I'm going to do is I'm going to divide it, and I'm going to think in terms of k. I'm going to think in terms of half-life. So let's just try figuring this out here. I'm going to do Carbon14 dating as a example of this. Carbon-14 dating is a way geologists use to actually figure out how old something has died off. Essentially how this works here is while the organism, let's say I have a tree, while the organism is living, there's always a very healthy equilibrium between the more stable carbon-12 form and the radioactive carbon-14 form. So carbon-14, having those two extra neutrons makes it unstable. While this thing here is still alive, there is an equilibrium that's set up. Note that as you learn equilibrium some more next year, equilibrium doesn't mean 50-50. It doesn't mean just because carbon-12 can convert to carbon-14 and interconvert, doesn't mean half of it has to be this, half of it has to be carbon-14. In fact, we know from the average atomic mass, carbon's weighted average is 12.01. About 99.9% of it is carbon-12. I only had the odd fraction of carbon-14. But so the story goes, as this organism here is still living, that equilibrium is constantly there. So as the carbon-14 decays away, the carbon-12 will naturally replenish that amount. Let's say I come along and I chop down this tree. Okay, so my tree here is no longer living. What's happened here is, now that my tree has died off, it actually loses the ability to actually do this replenishing. So whatever carbon-14 that I had at that moment that I chopped it down, this is going to be t equals 0, that total amount of carbon-14 will be at a maximum, and over time it's going to actually steadily drop off. By actually tracking the proportion, now fast forward whatever millions of years or whatever, if I can track how much carbon-14 is still left in relation to the carbon-12 is still left, I can backtrack and I can figure out how long ago was this thing, did this thing here die off. One sort of not obvious conclusion out of carbon-14 dating, you actually need to destroy your sample to actually do this. You actually need to burn it up to actually sense how much carbon-14 carbon-12 is. So sometimes if it's a really precious artifact, I don't want to actually burn it. So it would be nice if I can find another way to do this dating. But let's just try it here, carbon-14 dating. So carbon-14 beta decays with a half-life of 5730 years. Right? Obviously, nobody has sort of lived 5,000 years or so to track whether this is true. But if I get a sense of any potential part of this curve here, I can just sort of extrapolate. I can figure out, well, how long was a half-life? How long will I need to actually wait for half of the decay? Sometimes they're going to ask you, can you write the nuclear equation? That's what we practiced earlier. If carbon-14, we're told it does beta decay. For a beta particle, we know we put a 0 and a -1. What's my leftover? Carbon is element number 6, so I can find that on the periodic table. Because a neutron became a proton, I'm now going to have element number 7. Element 7 is now nitrogen. But because that electron, the beta particle, basically leaves with no mass, I'm going to still have 14 units of mass total. Again, this electron definitely is charged. The charge is implied. So charge is implied by this left subscript. I usually just tell people, well, this chemistry is getting so weird. What? We were carbon on the left and not carbon on the right. It's so strange already. Don't really worry about the charges. We can have gaining electrons, losing electrons in a later date. All right, so that's the nuclear equation. I'm told the constant, if you wait every 5730 years, half of it then decays away. Let's say in this question here, I want to know what percentage of carbon-14 remains, how much is left over after, let's make it here, 8,000 years. Right. So that's just the question. Do you always do a mental check for yourself? Sometimes they put you on an exact increment of half-life. We don't actually need to use this formula. In this case here, I like starting off with a picture. For carbon-14, I'm going to start off with an initial amount N naught. If I wait one half-life, I'm going to have 50%. Right? One half-life is 5730 years. If I wait another half-life, so in total, 5730 times 2. This one here is actually going to be 11460. It's going to now be 25%. Because 8,000 years, first thing, it's not super nice, but because 8,000 years is somewhat a little over one half-life, not quite two half-lives, I'm expecting something in between 25 and 50%. Because it's not on an increment of half-life, let's just do the math. So nt is equal to n naught, 0.5 t over k. They didn't give you any amounts because they just want to know what fraction is left over. You could put in an amount. You can say, pretend I have 100 grams, 100% or so. What's the nt that's left over? What we're going to find is, as I divide the n naught over, what is nt over n naught? What is my remaining amount divided by initial? Oh, that's actually just the percent already. So we don't actually need to put in numbers. We don't actually know what the sample is. If I can just do the latter part of the formula, 0.5, I've waited an actual time of 8,000 years. I couldn't care less what your half-life is. But when I divide it by 5730, if I just did this part here in the power, I go 8,000 divided by 5730, this part here is about 1.4, give or take. This actually gives me the number of half-lives. So I'm actually sort of thinking in units of half-life. I need to wait 5730 for me to drop by half. If I wait 8,000 over 5730, I've waited 1 and a bit half-lives, what we drew on the picture there, and that's actually going to be in the exponent when I do the rate. So let's just type that into your calculator. What is 0.5 to the power of this 8,000 divided by 5730? I'm expecting something between 25%, 50% here. Calculator gives you 0.3799, so let's give or take here. We have 38% left. That seems reasonable, right? So because it came out of exponential decay, at the beginning you're going to drop off faster than later on, I have to use this formula here. That's the easier way of wording the question here. I'm going to introduce to you the slightly harder way of doing it. The harder way is, what if they ask you, let's say part B of the question, I want you to actually figure out how long do I actually have to wait? How long until, let's say, 90% decays? Right? So again, I can draw a picture. I start off with 100%. After one half-life, 50%. After another half-life, 25%. Another half-life, 12.5. Every time there's a half-life, I lose half of it. So in this case here, I want how long until 90% decays. Make sure you do yourself a favor. 90% decays means how much is left over. This means 10% remains. I'm not going to punch in 90% to my formula. I actually want to punch in 10%. Based on my picture, it should be roughly 1, 2, 3 and a bit half-lives. Because the half-life is about 5,700, I'm expecting something upwards of 16,000, 17,000 or so. The math will tell me exactly what it is. Let's try it out here, and we'll finish off with this. And t is equal to n naught, 0.5 t over k. I could even put numbers to it, just to prove to you I didn't need to necessarily do a ratio. Let's pretend, sure, 100 grams. 100 grams is nice. I can say 100 grams here. I can put, well, 10 grams is remaining. Careful, this has to be remaining, right? Not the amount that decays. This is factored by 0.5 t over k. I just put in the units there just to show you when I divide 10 divided by 100, that gives you 0.1. That would have told you 0.1% remains. The gram would actually cancel the gram. That actually lets you do the exponent without any units. I want to know the actual time that I'm waiting, given that the constant for carbon is 5730. Again, every element has its own half-life. In this case here, it's just the math is a little hard. I am interested in finding the t. Only problem is this t here, not only is it in a fraction, it's up in the powers. What I need to do is I need to do the inverse operation. The opposite of an exponential function is actually the logarithm function. Now, I know some of you may not have seen logs in class yet, but basically we'll just treat it, logs do the opposite. So just like if I plus 5, how do I get rid of plus 5? Minus 5. If I multiply by 10, how do I get rid of multiply 10? Divide by 10. If I exponent to the power 3, I can take a logarithm base 3 to actually convert back. So I'm just going to walk it through as if you haven't done it. What I'm going to do here is I'm going to take logs of both sides. You can do natural logarithm ln if you want. In this case here, the operator is just logging both sides. And log really is just the opposite, the inverse operation of exponent. So earlier it was 0.5 taken to the power t to 5730. After I log it, it's going to undo this exponent. There's a log rule that says you can just bring that back down. And therefore, we've taken care of the problem that undid the exponent. That made the math really hard. But we need this log operator to solve the rest. And now we can solve our way for t. I'm going to bring the 5730 over to the left-hand side. I have a log 0.1 divided by a log of 0.5. Again, if you haven't seen it before, just press the log button in your calculator, and it's going to give you the answer. I'm expecting something over 16,000, 17,000 or so. 5730 times log 0.1 divided by log 0.5, and that gives me here 19,035, give or take. It's a little bit hard to do sig figs through an exponent or through a logarithm. So usually in the question itself, it'll say round it to the nearest year or round it to 2 decimal places, and you just round your answer to that case there. All right? So practice through some questions and let me know if you have any problems. Thanks, guys.